Okay, last time I proved the Laplace equation's maximum principle, whose statement was that if you have Laplacian of f equal to 0, then max and min of f cannot happen in the interior. So if you have a boundary condition, then, or if you have this being satisfied over a closed domain, then the maximum or minimum value of f can only happen at the boundary. And the important consequence of this was that if you have a Laplace differential equation on a domain and you have some boundary conditions, and if you assume that there are two different solutions, u1 and u2, then if you take the difference between them, it still satisfies the Laplace equation with the boundary values being 0. And because max and min cannot be other than 0 due to this theorem, you know that the difference function is 0 inside the entire domain, and therefore you have the unique solution. So this maximal principle gives rise to the fact that Laplace equations can only have one unique solution if it has one. Right? And since in class we came up with solutions for the Laplace equation for also the disk domain or the rectangular domain, we've been coming up with solutions. Always the question was whether the solution that we got was the only one, right? If it's not, then we have to work harder to find the other solutions, but this immediately tells us that the solution is unique. Okay, so that was why we like this theorem. But to prove this, I first proved the mean value theorem, which was that if you have, if it satisfies this, then the property is that the average value over the entire disk is same as the value at the middle. And this says, well, if the value in the middle is bigger or smaller than the other one, the neighboring ones, there's no way that the average of these things, I mean, if it's like a mountain peak, there's no way that the average will be the highest value, right? So the mean value theorem, once you prove it, it gives rise to this one. But I think it's also important to know why this is true in a very intuitive sense, because I gave you two different meanings of the Laplacian, right? So the first meaning was Laplacian is you first take the gradient vector field, right? And then if you take the divergence of the gradient, that's same as the Laplacian. And then you say that since it's equal to 0, it's saying that the gradient vector field is divergence free, which means that over any domain, the flux of the gradient vector field would be 0. That was one meaning of it. But then I also provided a second meaning, which was that for two-dimensional functions, the Hessian of a function is given as fxx, fxy, fyx, and then fyy. And the usual Laplacian is a trace of this Hessian, right? And if you just look at this notation, the Laplacian being fxx, fyy, these are second derivatives. Okay? And if the sum of these two is equal to 0, that means if one is positive, which means it's concave up in one direction, then in the y direction it should be concave down because they have to add up to 0. So if one's positive, the other has to be negative, right? So you know that at every point when this is true, it's like a saddle. Does that make sense? Right? So this should actually like obviously tell you why the max or min could only happen at the boundary. Because think about this case when you have a maximum inside the boundary. Then what's the second derivative? In any direction, if you cut this in any direction and you look at the second derivative, it should be negative because, come on, you know this, right? You know this picture? If the second derivative is negative, that means it's concave down. The second derivative is positive, is concave up. Right? So, if it's this case, then both fxx and fyy has to be negative for that to be true, right? Yeah. But if that's true, then there's no way you can have a Laplacian of f equal to 0 because both are negative. If you add them up, it will be negative. So that's like the very rough idea of things. Well, of course, things are not as simple as that because sometimes you might have a second derivative equal to 0 and still, so, like y equals to x to the fourth power, this graph would be overall concave up, but the second derivative is 0 at 0, so there's some problem with using this as a rigorous proof, but nonetheless, it kind of makes sense if you think about it. If it has a maximum inside the domain, then you're going to have a shape like that, and of course, the sum of these two will be negative, right? Also, if you had a minimum inside the domain, then for the same reason, the second derivative in the x direction and the y direction would both be positive, so there's no way that it could be equal to 0. Does it make sense? Right? Because of this, there's some related concepts to this one, which you don't get to see a lot, but it is kind of helpful later if you're going to grad school. So there's something called subharmonic functions. By the way, things that satisfy these are called harmonic functions. Okay? So f is called harmonic if it's a solution. If it's a solution to the Laplace equation. And there's something called a subharmonic functions. And those are cases where you have Laplacian of u greater or equal to 0. Now, we're using sub, but somehow it's greater. The reason being is that if you have a function like this one and function like this one, and if they agree on the same boundary, then inside the domain, you can show that this function will always be less than the other harmonic function. So subharmonic means that the function value will be somewhat less or equal to the harmonic function. Now, well, we don't really have to know in what context this comes up, but you can already see that what kind of property with respect to the maximum principle this will have. See, this also will not be able to have a maximum inside the domain, right? Because that also means the second derivative cannot be both negative. Is that right? Then what would be the condition that would force a function not to have minimum inside the domain? So this one will have no max inside the domain, only on the boundaries. What do you think the opposite would be? You would have a case where Laplacian of u is less or equal to 0, which is called superharmonic functions. So in this case, this prohibits both uxx and uyy being positive, because then it's not going to work, right? And that's exactly what happens if you have a minimum inside the domain, right? So this will be no minimum inside the domain.